Yeah.
Yeah. I think I'm gonna go ahead and get started here. I am hoping that most of you had a pretty good Thanksgiving. I see a lot of people wearing masks and quite a few people that maybe this time of year can be a little difficult, and we're all kind of stuck indoors and germs everywhere and so on and so forth. I hope that you're all staying healthy and ready to make a final push here through the last part of the semester. And I think things for the most part went okay while I was gone, except I screwed up with I didn't make a button to submit your exams into, which created a big problem for me, because then I was like, oh, I can't grade these exams. Well, I got most of them graded because you guys did a great job sending in your original in-class notes. And then I had to grade a few of them this morning. I have to admit, I just got back into town yesterday and I am not on top of things. I had about 80 papers to grade this morning, and that's like all I did. And so I'm not like in the position I'd like to be in with respect to, like, for example, working on your final exam review materials and all that stuff. So I need another 24, 36 hours to get on top of it. I have tomorrow completely free to do that. So I think I will get on top of it. But before I do that, I have to show you a few pictures from my trip. I went to, thank you. What are you using there?
Actual whiteboard wipes.
Oh, okay. Hopefully.
They're not as good as the extra ones.
Well, and I see that it's wet. I don't know, when is it gonna dry? Is it gonna dry before I wanna write on there? I'm gonna trust you.
It's not worth that to get fixed out.
Okay. Yeah, so, I love to climb mountains, and a lot of the mountains that I climb, I can do them in the summertime, but it turns out that the mountains I was climbing this time are the highest mountains in the world that I've ever climbed. And when they are that high, of course, they're covered with snow. And it is much better to climb snowy mountains when it is as cold as possible. That's because if it's warm, two things. First of all, if the snow becomes soft because it's warm, then you will sink in to the snow a lot, and it takes a huge amount of energy to pull yourself up and out through deep snow. So you don't want that. So you want the snow to be hard. Of course, you don't want to slide off of the snow, so you have to have crampons on your feet, and you carry an ice axe, which is what I was doing on this trip pretty much from the get-go. But the other way that they keep you safer is they send you to bed at about 6 p.m. You eat dinner at 5. At 6 p.m. they tell you to go to bed. Of course, nobody can really sleep, but you pretend to go along with the program. And then at about midnight, they wake you up and you start hiking. I took this picture at 3 o'clock in the morning. Somehow my phone did a good job. You see the stars up in the sky. These are the city lights of Quito. Quito is the capital of Ecuador. It's got about 3 million people living there. And this was the first, so I actually climbed 6 mountains. The first week we were doing sort of warm up, acclimating, getting used to the altitude. And then this was the first real big one. It's called Cayambe, and it's almost 19,000 feet high. And yeah, so we started at midnight and we were hiking up the side of the mountain here. It says about 3 in the morning. We're like halfway to the top or something like that. And then a few hours later, hopefully get to the top right about sunrise. This was balmy weather. This is the puffy. This is like I could wear a puffy around Orange County sometimes. It's cold at night. But yeah, we're all hanging out here on the summit. And I mentioned that there's 2 reasons why you don't want to climb something like this in warm conditions when it's too hot. One is, again, it's plodding through the deep snow. The second one, which is more serious, is that these mountains are always glaciated. So they're covered by glaciers, and glaciers have what are called crevasses in them. They have these gaps that are just abyss, basically. It's just open space that's sometimes hiding underneath the snow. And you can fall into one of those and it could be very, very catastrophically serious, especially if you just did it by yourself. So what you do is you put your whole team together and you all get onto a rope. The idea is if one person would happen to break into a crevasse, right, then hopefully hopefully you don't drag everybody else. No, if I fall into a crevasse, everybody else has to save my life by getting their ice axes out, getting down and stable on the ground, and then they can pull the person out, right? Whether they're conscious or not, at that point. Anyway, so that's why we're all kind of on ropes here. And of course, something like this, I would never do this alone. You would never do it alone. It would not be safe. So this guy over here was our guide, and he's been up the mountain so many times. He knows where the crevasses are, right? And he knows what time of day to get us up this mountain. But yeah, by climbing it in the colder time of the day, you're more likely to stay up on top of the snow the whole time. Yeah, Nikolai?
Are you legally allowed to go up by yourself?
In Ecuador, no. The same thing as in Tanzania when I did Kilimanjaro. That's part of their economy is and their work for their people there. In some places you can, like in Mexico, the high mountains of Mexico, you can go up there on your own. But yeah, I wouldn't do that. It's just not a good idea. So let me show you some more pictures here. I hope you guys don't mind. I have to show you a couple things. There I am on top. Yeah, so you can see these are the other mountains a couple days later. So I just did this one first and then I went over and did those others. So they're poking through the clouds, but yeah, it's like that airplane experience of being up above everything. And then, well, this one. Okay, thank you. This is the second mountain I did. This is called Cotopaxi. There's even a brand of clothing or something that's named after that. The people who are watching online. Another good reason to climb these mountains early in the morning is that the sun is so intense. There is very little protection from the ultraviolet rays at that elevation. So you can see like the sun is just coming up and I've got this buff around me and I had sunglasses. I just try to keep as little of my skin exposed as possible. But we're almost to the top. See all these huge icicles? It's hard to really appreciate it, but it's so beautiful what we were seeing up there. And so Cotopaxi is, it's about the same height as Kilimanjaro. And then the other reason I went to do these mountains now is that Cotopaxi had been closed for a couple of years because it is a volcano and it's very active. And so because it's active, it has a crater, and this is actually not a cloud. This is steam coming out of the crater of the volcano. And for a while, they didn't think it was safe to be up there because the volcano could explode like Mount St. Helens or whatever, but things had calmed down to the point that they reopened it about a year ago. So yeah, this is on the summit of the mountain with the crater. It's a pretty big, deep crater behind me there. But we got up there and we enjoyed a few minutes and that was fun. But then the real challenge, this is Cotopaxi as well. Obviously this picture was taken on the way down. This is very sunny now, very bright. But this is the front facade of Cotopaxi. Here's the trail over here that there's a couple people right there coming down. So it's a pretty intense thing. It's actually almost better to climb the mountain in the dark also, so you're not looking at it thinking what you have left to do in front of you. It's better not to know. It's like, I just want to see the next 2 steps in front of me. That's all I care about. So yeah, that is quite a mountain. And then we get to the biggest one of them all. This is Chimborazo. And on this one, we had a little bit of issues because the fog was coming in. We couldn't see great visibility. But I got to this point And this looks like a short little walk over. This is the actual highest point here. It looks like, oh, that looks easy. You have no idea how hard that was. I was so tired. This is 20,000 feet in the air. I've never been that high before. And just walking, if you had a 90-year-old grandmother walking on a sidewalk next to me, she would be beating me at my pace to go over to this peak over here. I'm not kidding. Like, it was that slow. You had to like just one foot in front of the other to get over there. This point is the farthest point from the center of the earth. It's farther than Mount Everest. And that's because the earth is not a perfect sphere. It's kind of a sagging, bulgy waste around the equator. So the great circle of the equator is actually much broader. It's a bigger diameter than any other great circle on the earth. And so, believe it or not, that point right there is the farthest from the center of the earth, or to say it a different way, it's the closest point to the sun on the entire planet. So it was kind of neat to get to do that. I felt very fortunate. This one, we were very cold. And this one, actually, one of our people in our group didn't make it. It was really, really exhausting. I mean, we had multiple guides and they're always prepared for situations like that. I wanted to turn, I was thinking, I didn't know if I could make it. So much of it, I just kept, they were very encouraging. They kept saying, oh, just take one step at a time. And it took like 8 hours of just doing that. And eventually we got up.
Didn't make it means they decided to stop.
Yeah. Oh, yeah. They're fine. They're fine. They just decided they didn't live in the time. Yeah. It's not that bad. I almost didn't make out. I will tell you, I was the old guy in our group too, so I felt like I had all the excuses to turn around, but I didn't. I just really wanted to. So there wasn't a lot of view at the top, but I did get to stand up there and kind of freeze for a few minutes. And then on the way down, of course, there's our whole group that we went up with. And even though the sun is not shining, you still have to cover up your body as much as possible because that sun goes right through those clouds. And then, this is me resting on the way down. You can see all of these cracks here in the glacier. That's something everybody's always so worried about on these mountains. So, this is crazy. It's quite an experience. Interestingly enough, though, as much as this looks like this is probably pretty hard, this was luxurious because every one of these big volcanoes had a hut that we could, the day before the summit attempt, we could actually hike up to this hut and sleep on an actual mattress and have somebody actually cook us some soup and some potatoes and some whatever it was, protein to get you going. And then the next day you just go do your summit and then come back down. Right. So if you want to climb something like Mount, Denali, for example, up in Alaska, you got to be ready to be out in the elements for 3 weeks straight, no break, carry all your gear with you, and you don't get to sort of have the comfort of a hut to get warm in. And so it can get a whole lot more interesting than what I did. There are some people probably laughing at me for making a big deal about doing this because really serious mountaineers would tell you that, this is kind of a cupcake, thing to do relative to what some people have done. But I did this partially to just sort of see what I was willing to put up with. If it was going to be totally miserable, I'd be like, okay, that's my limit. And I would say I was okay most of the time. I took Diamox, which is a medication that will help your body to sort of adjust to the altitude ahead of time. But unfortunately, the Diamox will also make you sick. So I got a little bit sick from the Diamox, which it gives you like indigestion and all this stuff. And so on the warm-up hikes, before we even got to the snowy volcanoes, on the warm-up hikes, I was like kind of throwing up and stuff on the trail at the first couple of hikes. But then when I did these mountains, I felt great. And everybody on my group had a problem with one of the mountains. Nobody made it through like all of them easily. So somebody got sick each time. But it was not me on the big ones. I got sick, like, probably everybody was looking at me on day one, like, he's already in trouble. He's not gonna make it. But I actually started feeling better, he seems, because I took the medication. Anyway, that was a whirlwind trip. It was not maybe a relaxing Thanksgiving. You know, you guys were all having turkey and mashed potatoes and gravy. I was like thankful for a piece of bread. And then Nikolai.
Was it hard to move?
The altitude, it was more than 1,000 feet higher than Otopex. So they sort of worked you up one peak at a time and a little bit higher each time, but that last one was a big jump. I was not feeling sick though. I was just tired, and everybody was.
Was
It's
it?
hard to breathe. So I was sucking this dry air in and out of my lungs. I actually have a little bit of a leftover cough. I'm not sick, but you might hear me cough a couple times today just because the air in my lungs was it was so cold and for so long, it was kind of a little tough to deal with. But yeah, that was quite an experience. And I want to thank all of you guys for I wanted to sort of test this out, see if I could possibly do this without having to like totally quit my job first. And I think it went okay. It sounded like other than the screw up that I made with the Canvas button for you guys to submit your exam, everything seemed to go okay. I graded the exams now. I think they're all pretty much, most of them ended up getting graded in Canvas actually. Lots of really good scores. There were a couple people above 90, but there were a lot of people above 80. You know, for the most part, I felt pretty good. I think maybe partially because there was a take home. The take home was pretty substantial in terms of the points. And yeah, I just feel like people were well prepared. The questions, nobody seemed like they had no idea what to do. So I was really happy with how that came out. If you do have questions though, of course, about your exam or anything about your standing in the class or whatever, feel free to stop by. I am back now and I'll be back obviously as we finish up the semester. We only have a couple weeks to go. I didn't have time, honestly, to get my final exam resources put together for you for this class yet. I will definitely have that done by Thursday though. That way you can start thinking about that. We have 2 homework assignments left. They are both going to be due on Saturday. I've decided and I'm probably going to throw in some office hours to help you with that. Just because I think this week's material, Tuesday, Thursday, then you have 2 more days to turn that in. And then next week we'll have another just like that. So that's pretty much all that's left as far as the homework goes. And I will be planning to do some review sessions and stuff before the final as well. So I'll get all those details worked out and get back to you about it. Okay, does that sound fair enough? There will not be a take-home part to the final. If you have another professor who's ever done that, I did find out that's really not allowed. The idea here is that we're not supposed to be giving people other work outside of class time to do during final exams because everybody's studying for their finals. I would like to honor that university policy. So I won't be doing a take-home part to the final. We will have, of course, more time to take the final. This is an hour and 15-minute class. You'll have the full 2 hours. I'll probably give you a little extra time like I always do. I don't even remember when the final is, right? I think it's on Tuesday, 2 weeks from today. Anyway, so I will put together a handout with sort of some information about that. I am going to do one thing though, at least one thing that I'm going to offer some extra credit towards the final exam for. And that is that I was looking this morning, not very many people have filled out an SOQ for this class yet. I really appreciate it when I get feedback. Like somebody who's told me once that it's great when I can record these lectures. Or they really liked having, quizzes or whatever the thing was. I mean, I really do read these feedbacks and I tweak my classes accordingly. But I would love to hear from you guys, things that you've liked about this class, things that maybe I could improve about the class. I mean, I really will take it to heart and read it. So here is the incentive. If I get 90% of the class to fill out a form. No pressure, guys. 90% of you to fill out this form. I'm gonna give everybody an automatic 3 points towards the final. So you don't even have to do anything other than fill out the SOQ form. I think as of right now, not even 50% have done it. You have until Friday night to do it. I cannot give you an extension on that because it's not my business. The university's got that all set up. So please fill it out, or your friends will be bothering you probably to get that done by the end of the week. I really appreciate some feedback. Okay, so just fill out, it doesn't take very long. Just take a few minutes and fill that out for me. I'd appreciate it. Yeah, I'd like to know what things have you liked, what things could I do a little bit better? Anything that comes to mind. Okay. Okay, so what we are gonna do, if there's no other logistical things to get into today, I'm going to talk a little bit about colorings of graphs. This is in chapter 12 as well. So we're going to take a look here at chapter 12.1. Wow, this is nice.
I took a picture of it and I showed Dr. Lesser.
Already?
Like, look at these differences. It's like something wrong.
Yeah. Well, he already probably knows. I went and complained to Renee already, so.
Oh, I walked right into Lester's office.
All right. So, excuse me, this is gonna be about graph colorings. And specifically, there's something we're gonna talk about here called the chromatic number of a graph. So this is kind of a fun topic. And so let me just draw kind of like I'm gonna draw just a map, if I could. So I'm just gonna draw like some regions. This is not obviously the United States, but it could just as well be, you know, whatever country you want to think of. Maybe it has some provinces or whatever like this. And if you were going to color this map with these different regions, you probably would try to not use the same color for two regions that are next to each other, because that would be hard to sort of tell them apart. So the idea here is to put a vertex in each region. So I can just kind of represent each region with a dot. So I'm just drawing a little visual to kind of get this conversation started. So we can just draw a dot in each region, and then I'm going to make an edge between any two vertices that are coming from adjacent regions. So like these two regions here on the left side of my picture, they should be connected by an edge because they are adjacent to each other, right? And this one would be adjacent to this one, right? This one is adjacent to this one. It's also adjacent to that one. This region is adjacent to this region. This one's adjacent to that and to that and to that and to that, right? And then these two are adjacent, these two are adjacent, these two. So you get all of these edges here, like so. Hopefully I've got most of them. Here's another one. But then the main thing is then you can just forget about the big regions and just draw the actual graph. I'm gonna start over and just draw the new graph that we've made without the underlying picture here. So it looks something like this. It's gonna take a minute to just kind of copy this graph down the way I've got it. Looks something like this. And hopefully I've gotten edges in there between everything that should have edges. Okay. Does that look about right? It's a little hard to tell. I probably should use a different color. Anyway, so there'll be some graph that's associated with this map that you're trying to color. And I think I've done it pretty close to correctly.
I think you're missing an edge in the.
This one, right? Yeah. Is that better? Yeah, okay. Other than that, I think I'm good. Okay. So with this in mind, the idea now is going to be to color the vertices. But if two vertices are adjacent to each other with an edge connecting them, we would want to use different colors because we don't want adjacent regions to be colored the same. So let's just write down sort of the rules of the game here. So we want to color this graph where each region is denoted with a vertex. So there's a vertex in each region here. With edges joining adjacent regions. So I'm just explaining how the graph was created. Edges are joining adjacent regions here, okay? And when we say color the graph, we're talking about coloring the vertices of the graph. Okay, so we're not coloring the edges or the regions. We're coloring this graph, and I'm just going to emphasize that here. Color the vertices. So it's the vertices that actually get colored in this process. Okay, so that's what we're going to be doing. And so I'm going to give you a definition then of what is a coloring. Okay, so we'll just have a quick definition, like what are the rules of how this is going to work. So a coloring, okay, a coloring of a simple graph. Simple graph just means no loops and no multiple edges, just a regular graph. A coloring of a simple graph is the assignment. We're going to assign colors here. It's the assignment of a color to each vertex, right? So that no two adjacent vertices, right, are the same color. Okay. No two adjacent vertices should be the same color. And sort of the goal of our little task here, the goal of what we're going to be doing when we're creating this coloring is we like to color the graph using as few colors as possible. Of course, if you just have a whole rainbow's worth of colors, you could just use a different color on every vertex and you'd be good. But the more interesting thing to do here, the goal is to color the graph using as few colors as possible. That's going to be our goal. So try to be efficient in our use of colors. So let's just try it on the graph that we have over here. And I'm colorblind, by the way. So this is going to be great for me to teach this. But what I would usually do is just label the vertices with whatever color I want to use. So maybe I'm going to use, I don't know, red would be R, and then blue, and then maybe we have white. So I could just label the vertices like so. And we just have to make sure that any two adjacent vertices are different colors. So you can see right away with this triangle that you need 3 colors, at least, right? So you need 3 colors, but when I get to the vertex that's up here, I could reuse the red again because these 2 vertices are not adjacent. So you would be allowed to use red there again. You couldn't use blue, but you could also use white in that case if you wanted to. And in fact, maybe it would be better. See, if I use red, well, I could go back to blue here. I'm sorry, I could go back to blue here. So that's fine. And then I could try to reuse the white over here. And then I could go back to the red here. And then I could go back to white right here. Okay, and then I go back to blue over here. So I think this is probably well, it is definitely as good as we can do. We cannot get away with fewer than 3 colors. And now we've shown a coloring that uses exactly 3 colors. Okay, so this is a coloring of this particular map that we've done using just 3 colors. And so this is something called the chromatic number of the graph. It's what is the fewest number of colors that we can use. Let me put that in the notes over here, maybe. So another definition. Is everybody understanding this so far? It's pretty clear? Okay, great. So the chromatic number. The chromatic number of a simple graph G is the least, it is the least number of colors needed for a coloring of G. It's just whatever the least number is, and there's a notation for this. This is written as chi of G. Chi is a Greek letter. It looks kind of like a curvy X. So chi of G, that's the chromatic number of the graph, right? So for example, in the graph above, chi of G would be 3. And we've demonstrated that we can color it with 3 colors, and it's fairly obvious we can't do better than that, because we have a triangle in there. Maybe a couple of other nice examples would be that we can use maybe some familiar graphs that we've looked at. What would be the chromatic number of, let's say, the complete graph on n letters? So if I had n vertices and I've got everybody's connected to everybody by an edge, that's the complete graph. How many colors do you think you'd need to use? Every vertex would have to have its own unique color, right? You could never use the same color twice because every 2 vertices are connected by an edge. So this would for sure just be n, right? That would be just n. Let's see. What would be the case of a graph that would have a chromatic number of 1? Let's go to the opposite extreme. In what situation would you be able to color a graph using only 1 color? Yeah, no edges, right? It's a null graph, a graph that has no edges. This would be if and only if G has no edges. So that's kind of another interesting case. Let's think about something maybe a little more interesting. Let's take, I don't know if I used this notation before. If I use C sub n for the cycle graph, I don't think I have. So let's just make sure that that's clear. So what this is this is just the cycle of n. So the graph of an n-gon. So C4 would be a square, C5 would be a pentagon, and so on and so forth. Then, so, if you want to kind of visualize this, you just have something, you just have edges kind of going around, something like that. This would be C7, for example. Let's think about what the chromatic number would be for the cycle graph. So why don't you take a minute and think about what it might be, how you could color this with as few colors as possible. Nikolai? Would it be just 2? Let's try it. So if I start with, I'm going to use white and blue. So I'll start here with white, and then I assume you're going to go to blue, and then white, and then we're going to go back to blue, and then white, and we're going to go back to blue. This one now has to be different, right? I would need 3 colors here. So it depends on what? Yeah, whether n is even or odd. If this was only a 6-gon, then we would not even have that vertex and we'd be just fine, right? So this is kind of interesting. This is either going to be 2 if n is even, and 3 if n is odd. So that one kind of depends on how many vertices you actually have. Okay, so that's a nice example of a chromatic number question. There is a famous theorem that is related to this chromatic number as well that I wanted to point out, and this was conjectured back in the 1850s. So this goes back a ways. This is a real problem, but it is called the four color theorem. And what this conjecture is that if G is planar, right, then it turns out that any planar graph can always be colored with four or less colors. You should never have to use more than that. Okay. Which, by the way, gives you another proof, a very roundabout way of proving that K5 is not planar. Right, because the chromatic number of K5 is obviously 5. This was conjectured in the 1850s. So it's a very old question, and it was finally proven. Just a little bit of background here. This was proven in 1976. So relatively recently, but the proof of this thing is basically a very computational proof that's done usually through a computer. So this is very computational, I'll just say. I had a friend who was doing his PhD in combinatorics at Berkeley, and he was getting antsy about finishing his degree, and he said that he asked his advisor, "What do I need to do to get my PhD and get out of here?" And the advisor said, "Oh, a one-page proof of the four-color theorem would be just fine." The thesis is going to be 1 page long, as long as it was just a nice, short, concise proof. No such thing exists, actually. So this is not a very satisfying proof, especially for somebody like me who's more of a theoretical mathematician, but it's just basically a massive case-by-case study. I've never really looked at the proof myself, but I can imagine it's not very interesting. So it's not one of those results that you get super excited about. Anyway, but it has been proven. And so if you have a planar graph, its chromatic number would be at most 4. So that is another nice result that's related to this chromatic number. Okay, I want to talk about are we okay so far? Good so far? Yeah, okay. I want to talk about the color partition of a graph. Okay, so a little definition here. So this is pretty straightforward. So if the graph G is colored with K colors, let's just say we're using K colors here. So if we color this graph with K colors, then we can partition. Partition just means break up into piles. So I'm going to partition the vertices. I'm going to partition the vertices. We're going to use capital V for that. We're going to break the vertices down into piles just according to the colors, right? So pretty straightforward. So if we partition this into K disjoint subsets, I'm going to call them V1, comma, V2, and comma, dot, 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 up to VK, with the union of all of those vertex sets, I goes from 1 to K, should be every vertex. So there should be no vertex that is without a color, right? Every vertex has a color. So here's the condition on those subsets. So the union of them is the whole thing, where all vertices in V sub I, all of the vertices that are in one of these components are the same color. So you put all of the red vertices into V1, and all of the white vertices into V2, and all of the blue vertices into V3, right? And so this is what is called the color partition. Actually, let's not call it the color partition. Let's call it a color partition. I would not claim that this is unique as to what colors go with what vertices. There would certainly be some choices there. But I should point out that within any given subset V sub I, there should be no edges. because those vertices are all the same color, so they should not have any edges in common. So if we come over here and we grab all of the red vertices, for example, so it'd be those three, there's no edges among any of the red vertices here. Same thing with the white vertices. There's no edges among any of the white vertices and so on. So that's, it certainly seems like it should be reasonable. Okay, so we can use this idea of a color partition to help us maybe figure out something about the chromatic number of the graph. The chromatic number is not necessarily K here. So this K is just, well, we've used K colors, but we're not saying that that was the best we could do. This is just, maybe we've made every vertex a different color and each vertex set has one vertex in it. That would still fit within this definition. But we can use the ideas here to help us with this chromatic number. I'm going to present a couple of theorems now. One of which is going to give us a lower bound on what the chromatic number of a graph would be, and then another one that gives us an upper bound. So I don't have like a one size fits all theorem, but we're going to try to get to some results here about the chromatic number. Look at this. Oh, wait a minute.
The whole thing.
Oh, I just see it. This. Oh,
It's just.
it might take me a minute.
Tried it. Wants to know.
No, because of what happened before.
I don't know what happened. The first half of the semester, I was not having any trouble. And I don't know who else is in this room. I come in here in the morning and there's this guy who teaches before me, but he doesn't use the board. He just uses his iPad, I think. And I don't know who else is in here, but they must be going crazy. I think the board just needs to be replaced. I actually do think so. So with you guys, I'm not so worried, but my other class, I'm like trying to get all the material covered and I'm like spending half the class trying to erase the board. This is harder than climbing a mountain. I'm certainly sweating more. You didn't turn on the air conditioning. Anyway, all right, I got at least it's decent. So here is this result that I was just talking about. So this is corollary 12.1.3. And so here's what this says. So let's let G be a graph of order n. So n vertices on this graph. Okay, and then now here's the tricky part is we have to define this symbol called Q. It's going to be a number Q, and this can be a little hard to determine, but let Q be the largest size. Again, you have to look at your graph and figure out what Q is. The largest size of a subset. The largest size of a subset of V. So we take a subset of V, which contains no edges. So you have to look at this graph. You have to inspect the graph and figure out what's the most vertices that you can take such that there's no edges among any of them. And whatever that number of vertices is, we're going to call that Q. And if we do that, then we can say something about the chromatic number of the graph. Namely, that it is greater than or equal to. So this is going to give us a lower bound on the chromatic number of G. And what we're going to put here is N divided by Q. So does it kind of make sense that if Q is bigger, if it's possible to find lots of vertices with no mutual edges, that you should be able to get away with less colors? Because you have many vertices that could all be done with the same color. because there's no edges between them. So you should somehow, if Q is larger, if Q is a big number, you would expect that the chromatic number of the graph could be smaller. It's not guaranteeing that because this is only an inequality, right? But at least it intuitively makes sense. If Q, think about the complete graph for a minute. And in the complete graph, Q would just be equal to 1. You couldn't ever take more than one vertex because anytime you grab two vertices, there's going to be an edge there, right? So for the complete graph, Q is only 1. And so, yeah, the chromatic number is very big, as we saw here a moment ago. So that kind of makes sense. The other thing I want to point out is, of course, the chromatic number is not going to be a fraction. So this looks like it could be maybe not a whole number. So we certainly can round up. If this comes out to, if we're saying that the chromatic number of my graph is at least 3.5, then we might as well say that it's at least 4. It has to be a whole number. So I'm going to do this thing called the ceiling of this thing. So that is, so this notation, I imagine some of you maybe have seen this before, but just to be totally sure, this is the ceiling of X. So that's just round up to the next whole number. So if it's a fraction, round it up. Okay, so let's do the proof of this. Maybe I'll do it over here. It's funny, yeah, I was able to erase that pretty quickly. I think the longer I'm in this room, the easier it gets for some reason. I mean, it still doesn't look very good, but anyway, it is what it is. You guys can see what I'm writing, I hope. You'll let me know if not. Okay, so let's try and do the proof here. Okay, so to do the proof, I'm just going to establish a notation. The chromatic number of G, I'm just going to call that K. And I'm going to create a color partition based on that, right? So I'm going to let V1, V2, and ... up to VK be a color partition. Okay, so we're using as few colors as possible, and we're now going to put the vertices into the piles according to those colors, right? So every vertex in V1 is red, every vertex in V2 is white, and so on and so forth like that. Okay, so then would everybody agree that Q has to be at least as big as each of these V sub I sets? Guys, remember that how many edges are there within V1? None. They're all the same color. There's no edges there. So however many vertices are in V1, Q, which is supposed to be the largest possible subset in which there's no edges, would have to be at least as big as this subset of vertices that has no edges. So that would be for V1 and for V2 and for V3. For each I, Q has to be at least as big as the null graph that you get when you look at the vertices just within one of the sets of this color partition. So everybody with me on that? This is actually the key point of the proof. This proof is not all that difficult, really, because if you believe that, do you believe that? Or should I explain it again? Let me explain it again. So within V1, just look at V1. Every vertex in V1 is red. So there can be no edges within any of those vertices, because remember, you can't have two vertices connected by an edge if they're the same color. So all of the vertices in V1 have no edges amongst them. So how many vertices is that? Well, that's the size of V1. Q is supposed to be the most vertices anywhere in the graph whatsoever that you could take in which you had no edges. Well, here's V1, which is a bunch of vertices in the graph that has no edges. So Q is at least as big as whatever that set is. And that's for any one of these vertex sets. Yeah, great. So once we sort of see that, then guys, we are good to go. N is the number of vertices, and as we know, that will simply be the size of V1 plus the size of V2 and plus dot 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 plus up to the size of VK. So all of the vertices are just in one of those camps. And each one of those VIs is less than or equal to Q. So this is just Q plus Q plus Q plus Q a whole bunch of times, and that's exactly K times. So that's K times Q by the time we simplify that down. And so K, if we now just solve that around, K is greater than or equal to N over Q. Just divide through by Q essentially. K is greater than or equal to N over Q, and therefore it's greater than or equal to the ceiling of N over Q because it has to be a whole number integer. And that's the whole proof. That's going to be the whole proof. Okay, so that at least gives us one bound on the chromatic number of a graph. It's bounded below by N over Q. The hard part about the corollary is just figuring out what is Q, right? What is the most vertices that you can collect together that have no edges amongst themselves? And that's really just by inspection. Like I don't have a, you know, one answer for exactly how you figure that number out. Okay. Does it make sense? Any questions on that proof? Okay, well, it turns out there's also a proof to go the other way. There's a proof to put an upper bound on the chromatic number of a graph, and I think maybe that would also be worth looking at. This one's actually stated as a theorem in the book. So this is theorem 12.1.5. And this one is actually, I think, an even easier result to understand. So this just says, you know, let G be a graph. When I say graph, it's the same thing as simple graph, right? Those two words are synonyms. So it's just any graph, such that, add a little bit here, the maximum degree of a vertex is, and I don't know why the book does this, but they use a delta for the notation. So this is just the some number. It looks like a triangle. So unlike the corollary over here, where it's a little hard to sort of just see what Q is straight off the top of your head, this is easier because the maximum degree of a vertex, well, you just look at all the degrees of all the vertices and just pick the biggest number that you see, right? So the largest degree. So then the conclusion is that the chromatic number of this graph, now I'm going to give you an upper bound. So we have a lower bound over here, right? And now I'm going to give you an upper bound. This is, turns out it's just delta plus 1. Okay, so it's a fairly simple formula, inequality, I should say. And the proof of this, I'm also going to present, it's really more of an algorithm. What this is going to do is it's going to show you how to color the graph using delta plus 1 colors. That won't necessarily be the fewest colors, which is why it's an inequality, but we're going to show you how to do this with at most delta plus 1 colors. So I'll call this a proof, but really it's an algorithm. Can you guys see this okay? The writing? For some reason, the blue is easier to erase. So I'm trying to maybe use that a little bit more here. Okay, so what I'm going to do is I'm going to label out my vertices. So label the vertices of my graph. I guess the graph will have order n again. It's not explicitly stated as such in the statement, but that's okay. So let's call them x1, x2, and dot, dot, dot up to xn. Those are the n vertices of the graph. And I'm actually going to start coloring the graph. Okay, I'm going to create kind of a process. And the first step of the process is to just take the first vertex and color it with whatever you want. Okay, so I'm just going to assign color number 1. You guys let me know if you're having trouble reading this. I'll go back to black again. but assign color number 1 to X1. So you just kind of randomly pick the first color, say red, whatever. Okay? And then next we're going to consider X2. And by the way, so you could have ordered these vertices however you like. There's nothing telling you which is the first vertex or the second or the third. You can use this algorithm regardless of how you sort of set up the labels on the vertices. And so you're just going through the graph as such. So here's what we're going to do, guys. It's sort of two cases. If X1 and X2 are adjacent, then you're going to need to use a new color for X2. Otherwise, you can keep reusing the old color. Okay, so let's just write that down. So if if X2 is adjacent, meaning connected by an edge to X1, right? Use color number 2 on X2. Otherwise, use color number 1 again on X2. So you can either, you just, the idea here is very simple. You just be as efficient as possible at all times. So if you have to use a new color, go ahead and do it. But to the extent that you can keep reusing the old colors, just keep doing that. Okay, so continue the process. It's almost just sort of a algorithm, as I said here. Let's consider Xi. We get to the ith vertex at some point along this algorithm here, right? Now, remember that the maximum possible degree of a vertex is delta. So the most vertices that Xi is connected to would be delta of them. So there are at most delta vertices that are adjacent to X of I. So you get to that vertex, there's at most delta adjacent vertices. And so there will be at least one of these colors among the delta plus 1 colors. So some color, this is the key point. So some color, either color number 1 or number 2 or number 3 or ... or all the way to delta plus 1. Some color in that list is not used. Come up here, give myself a little more room. Is not used by an adjacent vertex. There is some color that has not been used by an adjacent vertex. That's because there's only delta, there's at most delta vertices that are adjacent to Xi. So at most delta different colors are being used by the vertices that are adjacent to Xi. Is that clear? It's really mostly just a simple point. And so that means that I'm going to be able to use one of these delta plus 1 colors to color Xi, right? That's going to be the idea. So to wrap this up then, use some such color. There might be more than one option here, depending on exactly what the degree of the vertex is. Use some such color on Xi. Right? So out of this list, there'll be at least one of them available, maybe more than one. Just use one of them. And so you notice that this just goes all the way through the whole graph. The same argument. You never have to go beyond this many colors. This is just some fixed value here. And so that's it. Okay. So as such, we color G with at most delta plus 1 colors. Pretty easy. Pretty easy process. Okay. Yeah, I don't know that I necessarily need to do an example of that. I mean, you could just draw a graph out for yourself and just start coloring it. And anytime you have a chance to reuse a color that you've already used, do it. And if you follow that algorithm, you're gonna get a coloring that uses at most this many colors. Yeah, so it's pretty straightforward. Okay, is everybody good with this? Any questions so far? Not so good? Okay, so we talked about the color partition. We know what the chromatic number of a graph is. We've seen a few examples of it. I want to now turn to a slightly different question, which is not what's the fewest number of colors that I need to color the graph. Instead, what I want to ask is, if I have a certain palette of colors available to me, how many ways, let's get back to combinatorics questions, how many ways can I color the graph using those colors? Let's write that down as a question. So that's a slightly different question, but it's a very interesting one to think about. So I'm going to put that one right here. So given the graph G, is everybody still able to read this okay? If it gets too bad, you know, I think that board back there is perfect. I'm just gonna turn around and start using the back of the room. But let's see if this will keep working for the time being. Given a graph G and K colors, how many K colorings of G are there? I need to define what I mean by that. So a K coloring is just a coloring of the graph that uses some or all of those K colors. You don't have to use them all, okay? So a K coloring of G is a valid coloring. And again, two adjacent vertices have to be different colors, right? A valid coloring using at most K colors. Okay, so that's the definition. Probably should put that as a definition as well, but the definition of a K coloring, it is a valid coloring, meaning that you're not using the same color for adjacent vertices. But you're using at most K of the colors. You don't have to use all of them. Okay, so I'm gonna have a little notation for this, and then we're just gonna talk about some basic ideas here today, and only got about 12 minutes left anyway, so we won't get that deep into it for right now. But given your graph G and your number K, right? The number of K colorings is denoted by the following notation, P sub G of K. So you'll see me using this notation. So the number of K colorings of G, okay? So let me make a couple of basic observations first of all. If the K value was less than the chromatic number of the graph, okay, so let's be careful here. Remember, the chromatic number of the graph was the fewest number of colors that I could use to color the graph. Let's suppose I give you even less than that. So I give you less colors than the number of colors that you minimally would need to color the graph. So then what would be the value of P sub G of K in that case? It's just 0, right? You cannot color this graph with K colors if K is smaller than the chromatic number. It's exactly right. Clear enough? Okay, let's take another easy situation. I'll call this one an example. So if G has order n and no edges. Now, if there's no edges, then of course the chromatic number of the graph was equal to what was it? It's just 1, right? So we actually can get away with even just one color. But what do you suppose would be the formula for the number of K colorings? I have K colors available and I want to color all the vertices. And I really have no constraints because there's no edges. Anybody have a thought what the formula would be? So I have a bunch of dots. No edges, 5 dots here. How many colors can I choose for the first vertex? All right, any one of the colors, right? How about for the next one? Still K, right? Next one? Okay, it's all just K, right? K to the N, you got it. K to the N, that's the formula. It's very, very simple. So that's an easy case. Let's do the complete graph. That should be another one that we can do. Let's think about the complete graph for a second. I'll come back over here. Oy, 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 oy. Okay, so another example. Let's do the K sub n. So if we take K sub n and we use K colors, now remember, the chromatic number of the complete graph was already n. So this will be 0. For K equals 1, 2, 3, all the way up to n minus 1, it's going to be 0. But then after that, so maybe it helps to visualize it again. So if I draw my picture here, let's just draw the K5 just to have something to stare at. Think about this, and we've got K colors available to us. Okay, because of the symmetry of this, I don't really care where we start, just pick a vertex. How many choices am I gonna have, say, for the first vertex? K, right? What about when I go to the next vertex? I can't use the same color again, right? So I have to take that one out. K minus 2, so K minus 1. What about the next vertex? K minus 2, the next one? You're getting the idea, right? You just keep losing a color. And of course, if K is smaller than the number of vertices, you'll get a 0 eventually here. But you're just using the multiplication principle to make choices about the colors of each vertex one by one. So let's put the formula down. It is just this falling factorial that we've seen before. K times K minus 1 times K minus 2 and dot, dot, dot. The last one would be K minus N plus 1. Yeah, Julie?
So that means that this means that order matters. So you could be like K choose or N choose, like choose N, you know.
Right, if I go red, white, blue, green, yellow, right? That is different than if I do yellow, green, white, red, blue.
Okay.
Right, yeah, so we're assuming that the vertices of the graph are in fixed positions for now. We're gonna change the rules of that later on, but for right now, yeah, the vertices are set in stone exactly where they're sitting. Yeah, Maria?
I was just wondering about the K minus 2, because I understood like you have K choices for the first one and then K minus 1. So like say you did red for the first one
Red
and then like blue for the second
and
one.
then blue,
Wait,
okay.
couldn't you do red? Oh, never mind.
See, we have every possible
Yeah,
edge, right? So every time you go to a new vertex, you have to use a new color. Right, that's the trick. And so as you use the colors up, you'll lose one color each time you go along the way. Yeah. Don't forget why. Uh-huh.
And why isn't it, it's based on.
It doesn't have to be just one color. If we want to optimally color the null graph, we would just use one color on every vertex. We don't have to. That's why I've got K to the N here. I could choose blue for the first vertex and then maybe blue again for the second vertex. And then I could go to green for the third vertex. Right, I have that K choices every single time.
Got it.
Yeah, that's exactly right. Now, a much more interesting question, which I'm not going to get into now, and maybe I'll let you guys think about this one, would be to take our good friend, the cycle graph, and think about what that number of colorings would be. Turns out that I wouldn't spend too much time on this because it's actually fairly difficult. We are going to get an answer to this. We'll be able to rigorously do it, but it's going to come a little bit later. So let's just say for now, we need a couple more tools before I'm really fully going to be be able to explain that one. Let me just do, do I have time? Let me just do, yeah, 5 minutes. I want to do one more example that's not just one of these write it down immediately things. So let's actually draw a graph here. I'm going to draw kind of a triangle that looks like this. It's kind of standing on its side here. And then I'm going to add 2 more vertices way over here. And I'm just going to make kind of a trapezoid out of that part of the picture. This is going to be my graph. This is the whole graph. So I have 1, 2, 3, 4, 5 vertices. And just to help me talk about this, I'm actually going to label the vertices. So A, B, C on the triangle, and then I'm going to put D and E over here. So this is a graph that I'd like to play with here to kind of finish up the day. And then what I want to do with this is I want to figure out what is the chromatic. Oh, I haven't told you what this is called yet. It's called the chromatic polynomial of the graph. And the reason it's called that is because it turns out that this thing is always a polynomial. And we are going to prove that on Thursday. So here's a polynomial, right? Here's another polynomial. When I say polynomial, I mean polynomial in K. So K is like my variable that I'm talking about. So we're seeing that it's a polynomial in all of these examples so far, but I haven't officially written that into the notes yet. But we're gonna prove that next time. But let's take a look at this. Okay, so let's take a look at this one here. So this is a little trickier. Because, you know, I need at least 3, so I could have K choices, K minus 1 and K minus 2 for the triangle over here. It's like part of a complete graph. But then I come over to D and E, and what I do there is going to depend on like whether did I use the same color for A and D? If I did, then I have K minus 1 choices for E. But if I used 2 different colors here, then I would have only K minus 2 choices for E. So you get cases involved here. So what we're going to do here is I'm just going to, for the solution, just try to write some of this into your notes for you here. So after coloring A, B, C, and D, after we get those first 4 vertices colored, the number of colors for E, right, depends on cases. Okay, so I'm kind of focusing onto the heart of the matter here, first of all. So the 2 cases that we're going to have to do are case 1, A and D are the same color. And case 2 is going to be A and D are different colors. Obviously, these are the only 2 cases. Every coloring will either use the same color for A and D or different colors for A and D. So we kind of have to look at both of these cases. So let's do case 1 and case 2 and then add the results. So it's using the addition principle, the sum principle, I guess I should say. We're coming full circle, guys. We're doing combinatorics problems again. How many ways are there to do something, right? So I've got 2 cases. I'm going to figure each of them out and add the results. Okay, so in case 1, we have, so let's just work this out. K choices, I'm going to just kind of label here. When I color vertex A, I'll have K choices. Then when I go to vertex B, I'll have K minus 1 choices. Right? And then I go to vertex C and I'll have K minus 2 choices.
Dr. Annan, can you move
Color
your
vertex
laptop,
C.
please?
And then, okay, so I've used 3 colors here. So colors A, B, and C. Now, when I get to vertex D, I just have to avoid this color. Right? So I will have what? K minus 1 choices. So, oh, I'm sorry. No. I'm in case 1. In case 1, A and D are the same color. So once I've colored vertex A, I have only 1 choice for the color of vertex D, I have to use the same color again. That's what I meant to say. So I use the same color again. And so A and D are both the same color. So how many colors will be available for vertex E? K minus one, exactly. So there'll be a K minus one here for the color of E. So that's in case one. That's if we decide ahead of time that A and D are going to be the same. Okay, now let's do case two. I'm going to put it right below it. Guys, take your notes just in this same notation. So, because I'm just going to do this. Save some writing. I'm just going to go like that. So again, you know, color A, I'll have K choices for that color. Then for the second vertex, I'll have K minus one choices. For the third vertex, I'll have K minus two choices. Right, and so now I'm saying color D should be different from color A. So I can't use whatever color A is, but I obviously also cannot use whatever color B was, and these are two different colors. Because these are connected, so these are two different colors that we cannot use for D. That leaves us with K minus two colors for vertex D. But A and D have now been colored with different colors. So how many choices will there be for coloring vertex E? Also K minus two, exact. Right, and so that would be the ways of doing that. And so then the final answer, and then we're going to be done for today. The final answer then is to add up these two cases. So P sub G of K would be, case one was K times K minus one times K minus two times K minus one. And to that, we would add the second case, which is K minus one, and then we actually have K minus two 3 times. So I'll put that as a cubed. And you could certainly leave it like that. I'm going to just take a second and factor it. So we can factor out K and K minus one and K minus two. And so this is just algebra here. Just going to kind of clean this up a little bit. So I'll have a K minus one from the first case. And from the second case, I'll still have 2 more factors of K minus two to put in there as well. And so that would be the answer. And again, it's a polynomial in K. So every single time we have one of these graphs, we end up getting a polynomial in K. And that's going to turn out to be a pretty big theorem in the theory of colorings of graphs. So we'll do that on Thursday. And I'll try to get back to this question here on Thursday. I know you're waiting with bated breath for the answer to that as well. Oh, thanks, guys. Appreciate it for a great day. I will be downstairs. If anybody's starting the homework and wants to just have some moral support or some real support, I'll be there to help. And I'll look forward to seeing you soon. Bye for now. Did I give back all of the let's
Yeah.
Luke, were we just in a standoff?
I think this was
Like,
marginally successful, actually.
I think
And this
it's
board
like-
looks a whole lot.
This gets really concerned, but I'm like, look, I just made it, shouldn't be that bad. It should not be that bad.
I think the wipes don't work the way they're supposed to. But I don't know what to do. Everything.
Getting me the expo, like.
The monitors.
The markers and the wipes.
I
The wipes were the knockoff brand, so I'm like,
know.
can you just not cheap out and maybe then the board would look good?
I am not the cheap guy,
No.
trust me. Talking to Dr. Glesser. Okay, well, we'll gang up on him, I think. Okay, good.
You know what? Erase that.
You want me to erase it first? Or you want to get it before it's erased?
I wanna get the after, cause I wanna show them like, look, this was before Annan even started writing on it.
Oh, this is erasing a lot better though now than it was 10 minutes ago.
But still, the like.
No, it's
shouldn't
not
be
good.
that bad.
It's not good. This is
And-
reminding me of that classroom I was in last year, which was awful.
Well, that room was terrible. That was absolutely awful.
Sorry, I'm getting all this on recording.